In this video, we'll present the solutions to section 3 from the 2017 exam. This is one of the top 3 questions selected from the long answer part. So for each of the integrals below, and there's 2 in this section here, we're going to compute them, compute their value if they exist, or if they don't exist, we'll say that the integral diverges. So we note immediately this is an improper integral because of this infinite quantity. And so the first step in this process has to be, every single time, to get rid of that infinity, because that's our representation of what we mean, but not what we can actually calculate. And so we replace it with some value, and we later on take that value and make it larger and larger and larger. So that is how we would apply the definition of the improper integral. Next, we can take a look at the actual evaluation of this integral. And there's many different ways to tackle this, whether you want to do it all in one line. Here I'd be tempted to do it on the side as an indefinite integral, where we have the function itself. We don't worry about the limits of integration for now. And the reason it's helpful to put this on the side is because we have to do a few steps. This will require integration by parts. And what we'd pick here is, based on your experience from the fall term, pick u equals to t, and dv equals the exponential part, e to the minus kt dt, and we integrate the dv parts, and we differentiate the du parts, or the u part. Differentiate, integrate, being careful with our integrals. This is a negative k multiplier for the t. When we integrate, those constants come in the denominator because we're anti-differentiating, and then we can use our integration by parts formula to replace this integral here with t times e to the minus kt over minus k minus the integral of e to the minus kt over k over negative k and times dt. And if we have that, we can take it one step further. Let's call this negative t over k e to the minus kt, just reorganizing that term. And we get a double negative here, so plus 1 over k, then our integral of our exponential. And one last line. We have 1 over k already. If we integrate this, we're going to get the same exponential back, but divided by another negative k plus a constant. And now we can then replace the integral we have originally with this antiderivative. So we take this and use it as our integration step. Copy the limit down, we'll evaluate it later. Replace this whole integral with this expression here. Just being careful to include all the values. Here we have negative 1 over k squared e to the negative kt. We don't need the plus c because we're doing a definite integral here, evaluating it between b and 0. Just move this little connection line out of the way here. All right, so that's the antiderivative step. The second step is to plug in the limits of integration and get the actual area between 0 and b under that graph, while we still copy the limit down. And if we put in the upper limit for key ingredient here, make it more explicit, our integral was dt, so t is getting replaced by the value b, and then t is replaced by the value 0. So we'll have negative b over k, e to the minus kb, minus 1 over k squared e to the minus k times b, minus what we get when we evaluate that at 0t, that'll be 0 minus 1 over k squared e to the 0. All right, almost there. We just clean this up a little bit. We then look at all the places where b occurs. So we see b's here, here, and here, and this term is actually fine. That's just a 1. So at the end of the day, as b gets larger and larger and larger, here we have a negative exponential. That expression is going to go towards 0 as b gets larger and larger. This expression here You can confirm it with L'Hopital's rule, but we've also seen it frequently enough that a multiplier times an exponential, the exponential is the most important thing in that partnering. So this whole expression is also going to go to 0 as b approaches infinity. And with that calculation done, we actually have two terms that go to 0, a third term that went to 0, and we're simply left with 1 over k squared. So you'd say that the integral converges to 1 over k squared. And we're good to go. Moving on to the next integral. Here we have an integral that's not as obvious in terms of type. It's not even obvious necessarily that it's an improper integral. However, if you evaluate sine of 0 and try to imagine what the value of this function was, sine of 0 is 0, and we're dividing by that. So 0 is actually a problematic point here. That means cos of 0 over 0, sine of 0, is not defined. And that's what makes this an improper integral. And so the first step has to be, let's use a here, just custom, you can use whatever you like, but a is the lower limit of integration is usually what we say. We're going to let a go to 0 for this integral. Now instead of 0 at the bottom, we're going to use a, pi over 2 on top, cos of x, sine of x, dx. If we want to be extra special, what we can do is reinforce the idea of what side we're approaching that 0 value from. If we have our interval here, and presumably this function goes off to infinity or does something undetermined at the point 0, what we are doing is we're capturing the area underneath that graph up to some other finite point a, and we're going to let it approach 0, but only from one side here. It doesn't make any sense to have a straddling that bad point, so we would technically include a positive sign to indicate that we're approaching 0 from the right. That is not something we worry too much in practice about because it sorts itself out during the actual limit calculations, but that's why it's there in the solutions. All right, so we've applied the definition of the improper integral as our first step. We now have an integral that would be defined and be a nice finite area. We just need to find the antiderivative of what we have here. So again, as another role model for this approach, we can focus our attention on the antiderivative step as an indefinite integral first and ignore the limits of integration. We'll bring it back before we're done. In this case here, we have not an integration by parts, but I would say a fairly clear indication of integration by substitution. We have a function inside the denominator, sine, and we have it multiplied by its derivative, cosine. So if we do a substitution, and for that substitution, we let w equal the inside function, so sine of x here. We're going to get dw dx is cos of x, or rearranging that, 1 over cos of x equals, dw equals dx. That is what's inside our integral. So we can rewrite that using our substitution. We'll have cos of x, that's not really in our thing. We do have sine of x though, so we'll have cos of x, and sine of x is now what we're calling w. And we'll have dx, which is 1 over cos of x dw. That did exactly what we wanted. We cancel our cosines, and we end up with the ln, or 1 over w first, the integral of 1 over w, dw, those match then, and so we're going to get ln of the absolute value of w plus some constant. That's our antiderivative of the generic function there. We can then bring that over and use it to help us evaluate this integral. We're going to integrate the same thing. That's going to give us, we should probably go back to x's here. We weren't quite done. We have ln of w, but that is ln absolute value of sine of x plus c. That's better. That allows us to do the antiderivative step here. We're going to have ln absolute value of sine of x plus c. So we don't need the plus c because we're going to evaluate that at pi over 2 and 0. We're going to take the limit later. For now, we're going to evaluate this at pi over 2. And sine of pi over 2 is just 1. And then we're going to subtract, oh, this is an a, not a 0. Then we include the a value, so ln of sine of a. And that is going to be a challenge. Actually, we don't need the limit. We're going to evaluate the limit now. As a approaches 0 from the right, sine of a is going to approach 0, and ln of sine of a then, ln is undefined at 0. If you think of the graph of ln, as you get closer and closer to 0, that is going to approach infinity. And so what that gives us here is that the integral, in this case here, diverges. It doesn't go down to some finite value as we push this a value towards the problematic point at x equals 0. We get a limit that's undefined. And those are two examples of how we can carefully evaluate improper integrals.